Hello friends, in this video we are going to study example based on exponential Fourier series. So we are going to find out the exponential Fourier coefficient for the given signal. So here we are given with a rectangular signal whose positive cycle starts at minus 2 by 2, ends at plus 2 by 2, and the total period of this signal is given as capital T. So first of all, let us write the equation for exponential Fourier series. So exponential Fourier series is represented as x of t equal to summation n equal to 1 to infinity. It is not 1 to infinity, it is minus infinity to plus infinity. Cn, which is the exponential Fourier coefficient, e raised to j n omega t, where now we are supposed to find out the Fourier coefficient Cn. So to find Cn, we must have the equation for Cn, which is given as Cn equal to 1 by t integration from 0 to t, that is over a single period, x of t into e raised to minus j n omega t dt. So now we need to add the values of x of t in this integration, and we have to integrate this x of t signal over a single period. So if we look at the given signal, so this positive half cycle, let us state it from minus 2 by 2 to plus 2 by 2. This will be your positive half cycle, and for negative half cycle the amplitude is 0, and for positive half cycle amplitude is a. So here we can split up this equation into two parts. Period of given signal is t, so it will be as it is 1 by t. Now this integration is going to split up from minus 2 by 2 to plus 2 by 2, where the amplitude of x of t is a into e raised to minus j n omega t dt, plus for the next negative cycle, where if you find out the coordinate at this point, this will be 3 tau by 2. So the next integration will be from tau by 2 to 3 tau by 2. The amplitude of x of t is 0 into dt. So if we multiply it with e raised to minus j n omega t also, because of the amplitude 0, the second term is going to become 0. So now let us evaluate this integration. So 1 by t, from the first integration we can take a common, so it becomes a by t, integration from minus tau by 2 to plus tau by 2 e raised to minus j n omega t dt. So let us take the integration of exponential. So it is e raised to minus j n omega t divided by minus of j n omega with the limits minus tau by 2 to plus tau by 2. So let us take this minus j n omega out of the brackets. So it becomes a upon minus j n omega t. And here we need to substitute upper limit minus lower limit. So it becomes e raised to minus j n omega tau by 2 minus e raised to, so minus tau by 2 becomes minus becomes plus j n omega tau by 2. So here we have the equation e raised to minus j theta minus e raised to plus j theta, but we need to we have the negative sign also common. So let us multiply, or we can take this negative sign common. So it becomes now a upon j n omega t. So let us multiply this negative sign inside the bracket. So we get the terms as, so first term becomes negative and second term will become positive. So it becomes e raised to j n omega tau by 2 minus e raised to minus j n omega 2 by 2. So now we have a standard equation sine of theta is equal to e raised to j theta minus e raised to minus j theta upon 2j. So let us rearrange this equation and let us substitute this exponential divided by 2j as sine theta. So we get a upon n omega t e raised to j n omega 2 by 2, this is the theta, minus e raised to minus j n omega 2 by 2 upon, so here j is already available, so we will take j at denominator and we need 2j, so multiply and divide with 2. So this second bracket we can replace it with sine of theta. So we get the equation as 2a upon n omega t into sine of theta is n omega 2 by 2. So this is our Cn coefficient in terms of sine. Now further we can replace this sine with sinc function. So we have sinc of theta is equal to sine of pi theta whole divided by pi theta. So let us rearrange this equation in this form. So we have Cn equal to, this is 2a upon n omega t. Now sine of, we need it as pi theta, so pi into n omega 2 by 2 pi. So here we have just arranged a pi term into it, whole divided by the same term pi into n omega 2 by 2 pi and multiply it with the same term, so pi into n omega 2 upon 2 pi. So this center terms becomes now sinc. So we get the equation as 2a upon n omega t. This term becomes now sinc of theta. So sinc of n omega 2 by 2 pi. So it is sinc now, not sine, into pi of n omega 2 upon 2 pi. So now let us see what terms are cancelling each other. So here pi gets cancelled out, this 2 gets cancelled with this 2, then we have n omega t, here also we have n omega t. So the remaining equation is a by t, it is a tau is remaining in the numerator, so a tau by t sinc of n omega 2 upon 2 pi. So this is the value of coefficient Cn. Now in this equation we can substitute the value of omega. So we have omega equal to 2 pi f, which is equal to 2 pi by t, which is the capital T is the period of given signal. So Cn becomes now a tau by t sinc of n omega is 2 pi by t into tau divided by 2 pi. So here 2 pi gets cancelled out and Cn becomes a tau by t sinc of n tau by t. So this is the coefficient of exponential Fourier series for given square wave. So this x of t becomes, so we have to finally represent the answer in terms of x of t. So our x of t is equal to summation n equal to minus infinity to plus infinity Cn. Now Cn is a tau by t sinc of n tau by t. So this will complete our answer. Now the next part in this exponential Fourier series is to find out the spectrums. Okay, before solving the spectrum, there is one term missing in this x of t equation. So here it is Cn into e raised to j n omega t. This term has to be written always. So this becomes x of t equation. Now we are supposed to find out the spectrums. So first let us start with the amplitude spectrum. So to find out amplitude spectrum, we need to find out mod of Cn. So if you look at the given equation, mod of Cn is nothing but a tau upon t sinc of n tau by t. So straight away we can find out the amplitude spectrum as it is a sinc function with the amplitude as a tau by t. So we have this axis as n, this axis as mod of Cn, 0. So if you look at this equation, it is a sinc equation. So we know that sinc has maximum amplitude at 0 and this n values will be discrete. So we get this kind of spectrum for the given equation. The nature of this waveform will be sinc function. So on. So towards left hand side also we have this kind of equation. In this way we get the amplitude spectrum, and second we need to find out phase spectrum. So for phase spectrum we need to find out angle of Cn, which is given as tan inverse of imaginary part upon a real part. So in this case we do not have imaginary part, so it is tan inverse of 0, which is 0. So we do not have any phase spectrum. So straight away you get the value as 0. So this completes the answer for exponential Fourier series. So just to summarize, for given square wave we are supposed to write the equation of exponential Fourier series, then we are supposed to find out the Fourier coefficient Cn, and then we are going to plot the amplitude and phase spectrum. But before plotting it we need to write answer in terms of x of t.